Welcome back to More Fun with Finance. I'm Dr. William Elliott in beautiful uptown Shaker Heights. So, this lesson is chapter 7 in your text. So, we're going to be looking at sensitivity, scenario analysis, break-even analysis, as well as just a brief foray into Monte Carlo simulation. So let me get out of the way here and swap the slides out for the office photo, and let's get started. So here we go. All right. This chapter, I'm only asking you to read the first two sections, chapter 7.1 and 7.2. Real options and decision trees are very useful, but this class is only a semester long. Real options we could spend an entire semester on. Basically, a real option is the ability to, for instance, abandonment option. You start a project and it's not going as well as you're hoping. An abandonment option means that you get some sort of, you're saving something out of it. And the ability to view this in the framework of an option helps to add value to the traditional net present value analysis. There's also an expansion option. There are a variety of other options that can be used. However, it's definitely not for the faint of heart in terms of the ability to work through all of these things. There are a lot of problems that we can run into with real option theory and applying it in the real world. One of those is that we have to actually have an exclusive use of that asset or the ability to expand. If anybody can expand, then it has no value to us. It's like an option that can walk away from us. So anyway, we're not going to delve into that, those two last sections, but we do want to talk a little bit about sensitivity analysis, scenario analysis, break-even analysis, and finally, Monte Carlo simulation. All right, so this whole idea is that a point estimate is almost always going to be wrong. So we want to stay away from point estimates to the degree that we can. Sensitivity analysis and scenario analysis are very similar. Sensitivity analysis just says, let's allow sales to vary by so much. Let's allow cost of goods to vary by so much. And then rerun our analysis using a best and a worst case scenario. And leave it at that. Scenario analysis, we have a little more detailed information. So we might know that a particular, maybe some competition is going to join the market, and how will that affect our ability to sell the product that we're developing for this particular project. So we have some idea of exactly what it is that's going to cause the change in revenue or the change in costs. Whereas in the sensitivity analysis, we really don't know exactly what it is, but we know that there's going to be some variation. We're estimating these things with some error, or trying to predict the future. And so we're just putting some boundaries around it. Whereas scenario analysis, we have some specific ideas. Break-even analysis is a little bit different. Basically, break-even analysis tells us at what point are we going to reach the zero NPV point. We don't want to go below that, but it'd be nice to know how bad does it have to get before we hit zero NPV. And then or actually, I don't need to go on to Monte Carlo simulation. We'll talk about that in a minute. Stewart Pharmaceuticals is the example that the text is using here. And so let's adopt that and walk through this example. So they're considering development of a drug that cures the common cold. Be a nice thing to have, right? Especially, how about maybe COVID? The corporate planning group, including representatives from all areas, and this is really important. You got production, you got marketing, you got engineering in there, have recommended to go ahead with the test and development phase of this project. So this is two phases here. There's the test and development phase, and then there's the production phase. So this preliminary phase will last 1 year and cost about $1 billion. The group also believes that there's a 60% chance that the tests will prove to be successful, and that means we can go into the production phase. That phase is going to require an additional investment of $1.6 billion, and production will occur over the following 4 years. So let's look at that particular part of it. So we're going to look at that production phase first. We'll come back to the other piece of it in a minute. So the production phase, if it's successful, we expect to see in years 2 through 5, remember it's 4 years, 2 through 5 are going to be 7,000 in revenue. I believe this is in thousands. 3,000 in variable costs, 1,800 in fixed costs, 400 depreciation, pre-tax profit of 1,800, tax rate at 21%, meaning we have $378 in tax bill, and a net income or net profit of $1,422. That's going to generate a cash flow of $1,822. Remember, this depreciation is a non-cash expense, so that gets added back to the $1,422 to arrive at the $1,822. And of course, the first year we have the $1.6 billion investment. We're assuming a cost of capital of 10% here. So when we do the math, years 1 through 4, remember that sigma is a summation symbol in mathematics. And so we're going to take that 1822 cash flow and discount it at 10%. And we're going to do that for each of the 4 years. And we're going to add those all together. And then we're going to subtract from that the initial investment of the 1.6 billion. And we end up with a positive NPV of 4.175 billion. Okay, that's if it's successful. Okay. If it's unsuccessful, though, we're still going to generate some revenues. They're just not going to be anywhere near as much. So revenues are going to be 4,050 or 4 billion, 50 million. Variable costs of 1,735. Again, the same fixed costs, same depreciation. This leaves us with a pre-tax profit of 115 million. And then our tax bill will be 24.15, leaving us with a net profit of 90.85. Add back the depreciation for a cash flow of 490.85 million. If we take that over the 4 years and we do a present value, sum each of those present values up, add them together, or rather subtract them from the, or subtract the initial investment, we end up with a negative $44.07 million NPV. Now, so we've got, it looks like, hey, if it's unsuccessful, it's not a good deal. But the successful branch of this is actually quite lucrative. So how do we handle this? Well, what we're going to do is a weighted sum of the NPVs. So if it's a 60% probability of success times the NPV in that setting, 40% probability of failure or unsuccessful, and a loss of 44 million in that setting, we put those together and we come up with a positive NPV of $2.487 billion. Now remember, that's still out at year 1. We have to bring it all the way back to year 0, where we're making this decision. So here we are discounting that back for 1 year, and then we're subtracting from it that initial phase, that testing phase, the 1 billion from that, and we end up with a positive NPV of 1.26 billion. So, yes, we should do the test. All right, that gives us some confidence that we should do the test. Sensitivity analysis, though, causes us to be a little cautious. So here what they've done is they've said, well, let's suppose that revenues are not 7 billion, but only 6 billion. What would that do to us? Well, let's figure out the percentage change. That's about a little over 14% decrease in revenues. How does that affect the NPV, though? These things are not necessarily going to translate through the income statement linearly because we've got those fixed costs. That's going to make a difference, right? Well, it turns out that when we go through and we calculate the NPV using 6 billion instead of 7 billion in the successful outcome, we end up seeing the NPV dropping by nearly 60%. So for every 1% drop in revenue, we can expect about 4 times that for a decrease in NPV. So sensitivity analysis is important. You can't just expect that the change in revenue is going to translate through to a similar percentage change in NPV. It's not how things work, especially when you have operating leverage, especially when you have financial leverage. There's usually a magnification as you go down through the income statement. Scenario analysis, on the other hand, though, here's how it differs from sensitivity analysis. The sensitivity analysis, remember, we just assumed 6,000 or 6 billion instead of 7. Why? We don't know, but we know that there's a potential that we won't get the 7 billion. Well, here they've actually put some actual scenarios, some actual thinking to how this could be changed. So one scenario would be the next few years have heavy cold season and sales are expected to exceed the expectations. But as a result, because so many people are out of the workforce, the cost of labor goes way up. Okay, so that's an interesting scenario, right? It's not quite the same as just a simple sensitivity analysis. Scenario 2, the cold season is normal and sales meet expectations. Well, that's kind of our baseline that we already have, the one that we just looked at. And then scenario 3, the next few years will have lighter than normal cold seasons and sales will fail to meet expectations. And we may actually be able to put some specific numbers to that. They also mention other scenarios could apply. Maybe there's a problem with FDA approval that puts it off for X number of months or even years. These approval processes do not happen quickly. So we would calculate an NPV for each of these possible scenarios. We might even put some sort of probabilistic estimate on each of the scenarios. How likely is the heavy cold season? How likely is it that it's going to be normal or lighter? And historically, we could certainly look back and get some sense of how many times over the last couple of decades that occurred. So scenario analysis is a little more sophisticated than just a simple subtract off, $1 billion and call it good and take a look at it. Break-even analysis is yet a different animal. We have several different directions we could go. We could look at an accounting break-even analysis where net income simply is equal to 0. At what point will net income equal 0? Cash break-even, so sales volume at which operating cash flow equals 0. And then finally, financial break-even, where sales volume is at such a level that the NPV is equal to 0. All right, so we're going to look at an example where it's the NPV. It's this financial break-even. All right, so here's how to do this. This $1.6 billion investment is going to last for 4 years. And so what we do is we say, well, let's figure out what payment it would take in order to come up with a present value of 1.6 billion. Remember, we're still using our 10% discount rate. It's for 4 years. Future value is 0, so we're assuming no salvage of any sort. And so plug in the first 3 numbers and compute a payment. Well, it turns out that that payment would be 500 and just a little under $505 million per year. So now we can use that to take a look at our operating cash flows. All right, so if our operating cash flows are $504.75 million, what sort of revenue does that lead to at the top of the income statement? So here we are at the bottom of the income statement. We subtract off of that 504 the 400 million in depreciation, and that gives us a net income of $104.75 million. And then we work our way back up the income statement. 400 is fixed, 1800 is fixed, but obviously our taxes change. Our EBIT is going to be different because our variable costs are different. And then we can calculate a revenue at which we will break even with our operating cash flows. So that $5.332 billion equals to the 700 million doses sold times the price. So what we're backing into is how low a price could we charge. If we remember, we assumed originally here that we were selling at $10 per dose. But what's the minimum price that we could charge that would still give us a NPV of 0? And the answer is $7.62 per dose. Okay, so that's a break-even analysis. Monte Carlo simulation. I mentioned that in the last chapter, in chapter 6. It's a very valuable tool. This Monte Carlo simulation is really more related to that sensitivity analysis that we talked about at the beginning of the chapter as opposed to scenario analysis. We could certainly do break even. We could even do scenario analysis, but we'd still have to estimate the distribution of the various inputs to the model. But it is the name actually does come from the casinos in Monte Carlo, and it's another way of estimating how well you might do in a game of chance. So the example your authors give is, suppose that you're a blackjack player. You could play 1,000 hands for real money and find out, whether you should take a third card when the first 2 total 16. Well, that's probably a good way to lose a whole lot of money. So why don't you do it just without money? Do it with practice hands 1,000 times and see which creates the highest value, whether you take the card every time or don't take the card. And we're going to use the same technique, but we're going to apply it to a capital budgeting problem. In this setting, we might have a distribution for sales. Suppose that distribution is a normal distribution. We have a distribution for costs. Maybe it's a uniform distribution. We could even, obviously, we'd still have our interest charges. We'd have our taxes in there. We'd get to net income. We'd calculate a operating cash flow. Another thing that we could parameterize, though, would be the discount rate. How accurately are we estimating the discount rate? That's going to make a big difference too. So why don't we use a chi-squared for the discount rate? It's kind of a weird looking chi-squared, but you get the idea. It's actually it should be more like this. Get rid of that ugly one. Yeah, that's a little closer. I'm no artist. All right. We input those and then have it calculate an NPV on the basis of these three variables. So this would be revenue, this would be cost of goods sold, and this would be the discount rate. So then we let the computer draw out of each of those three distributions, run those values through the model, through the income statement, calculate the operating cash flows, and then discount them, subtract off the cost of the project, and save that value. Actually, let me just have you watch this YouTube video from the at-risk folks. This is originally developed by Palisades as a software company. It's now owned by somebody else. But let me just turn on this video and let you watch the actual process as it happens in Excel.
At-risk is a Monte Carlo simulation add-in to Microsoft Excel that benefits anyone who faces uncertainty in their quantitative analysis. By producing a realistic picture of all possible scenarios, businesses can protect against risk and identify and exploit opportunities for growth. Monte Carlo simulation performs risk analysis by substituting single-point estimates of uncertain inputs with ranges of possibilities. These distributions are randomly sampled many times, from thousands to millions of iterations, and the model recalculated to create large sets of potential future data, which can then be analyzed. Define uncertain variables with probability distributions from the palette, selecting parameters and truncations, names, and static values where appropriate. Then click OK. Distributions can also be fitted to historical data in a few easy steps. Select the data, select Fit, choose all distributions, or shortlist them, and include the desired boundary conditions. Click OK and let at-risk do the rest. Distributions are ranked using any of several fitting criteria and can be compared visually with overlays before selecting the best distribution. At-risk industrial gives you access to time series models, which can be defined directly or fitted to historical data. Choose the models you wish to fit and any transformations required. Then choose the best fitting time series to use in your model. Inputs can easily be correlated using at-risk. Simply select the distributions, then create your matrix. Coefficients can be entered here in the Define Correlation window, or directly on the spreadsheet. See the joint distribution as an indicative providing the best policy for your organisation in any situation by combining optimization algorithms and simulation techniques. One classic example is the product mix problem, where limited resources need to be allocated across multiple product lines to maximise your returns. Due to uncertainty in the unit costs, each decision has a range of possible outcomes. In the model definition, you can choose to maximise expected returns, minimise your risk, or optimise several other criteria. Constraints, both physical and business decisions, can be included in your model. Efficient frontier analysis is also available. Watch your outcomes improve in real time as at-risk optimises your decisions.
Okay, so that was the at-risk. That's their basically their pitch for why it's a useful piece of software. Now, this is definitely not an ad for at-risk. I've used it in the past. I think it's a great tool. There are a variety of other producers that provide similar types of software out there. Some of them are also plugins to Excel. So you can still be working in a setting that you're already familiar with, but gain this, as you can see from this, a very, very sophisticated sensitivity analysis. And that's about it for Chapter 7. Remember, this is only 7.1, 7.2. By the way, I did not assign any homework problems out of Chapter 7. So if you are just thinking I missed it, the answer is no. I just want you to know about these sensitivity techniques. I'm not going to ask you to actually implement them in homework problems. So make sure you read the chapter. Make sure you understand the terminology and the difference, say, between sensitivity and scenario analysis. But you're not going to be required to work any analytical problems with them. Thank you so much, and have a good evening. Bye-bye.